So far, in porous media flows, we have seen different uh, basics of the flow, including Darcy's law, continuity equation, and transport solute transport equation in porous media. We also understood what is porosity or how porosity is defined or calculated in porous media, permeability, hydraulic conductivity, etc. So they are all basics which you need to understand flows in porous media. So in today's lecture, we are going to study a dispersion in porous media. And dispersion is related to miscible flow. Okay, so when a particular fluid mixes with another fluid, or a solute mixes with the fluid in porous media, we call it miscible fluid flow. Okay, and that is what we are going to see in today's lecture. Okay, so in fact we can call it miscible flows. Okay, so to understand dispersion in porous media, we first need to understand this thing that's called molecular diffusion. And to understand molecular diffusion, let's take this example which we have already considered in the introduction of the lecture. So if you take a sugar cube and put it in water, fresh water, you will see that with time this sugar actually starts mixing with water, and as you give it more time, if this is time t1, this is t2 greater than t1, this is t3 greater than t2 greater than t1. So if you give it more time, slowly this sugar mixes in water completely, right? Even if you don't do anything, if you don't mix it, then also it will mix it spontaneously by itself, and that process is called molecular diffusion, right? Because the solute particles are actually moving from the region of higher concentration to lower concentration because of a thing called chemical potential. So basically there is a potential gradient, and that potential gradient is because of the concentration gradient. Okay, and that is driving this process, this diffusion process of the solute molecules. So this happens even when there is no velocity, or even when you don't apply any external force, right? In fresh fluid or clear medium. But now let's consider this porous media example. So we'll assume that this is porous media, and you have these are all porous beads, right? So we assume they are porous beads, or this medium is porous, but I'll not draw it. So in this porous media, let's consider that we have two regions. One is, the left region is salt water, or left side of the medium, porous medium, is filled with salt water, and right side of the medium of porous medium is just fresh water. Okay, so left side has zero concentration of C naught, and right side has the concentration of 0, so that's equal to 0, right? And let's assume there was a barrier in beginning. So there is this barrier, right, at t equal to 0, and now you remove the barrier. Okay, remove the barrier. So what will happen once you remove the barrier? The solute molecules from the left hand side will start diffusing to the right hand side, right? Because of this same process that's called molecular diffusion. And after time t1, let's say this is t1, which may be 1 minute, 2 minutes, or 10 minutes, you will see that the solute actually has diffused from right to left, right, this way. And because of that, there is diffusion or a moment of water molecules, and that is why there is a kind of mixing zone that is forming between this salt water and fresh water, right? And this mixing zone here has certain thickness. So you see this thickness here is, let's say we call it L1. Okay, that is the diffuse zone after time t1. This is without any flow. Okay, without any fluid flow. But now let's assume that you keep it under flow conditions. So if your providing some flow condition, and now your complete fluid system is moving, or this porous media saturated with fluid is actually moving. Okay, so there is fluid flow through the medium. So what happens in this case is, this fluid that is flowing here, as you can see, this goes forms different streamlines. So these actually go and kind of hit each other, right? All these streamlines that you see, this will go here, it will come here, this will hit each other. In it actually, the hitting of these streamlines with each other works like a mechanical energy. Okay, release of mechanical energy due to these uh, solid particles in the porous medium. Okay, and that actually enhances the rate of mixing, and this is equivalent to this external force that you apply to mix sugar or salt in glass of water, right? So this example that we are considering here, right, this example, so it is mixing slowly, but if you want to speed up the mixing, you take a spoon and you stir it, right? That increases the rate of mixing. So same thing happens here in case of more porous media. You're not really providing an external force or mixing effort yourself, but due to this tortuous path within porous media, these streamlines of fluid actually hit each other, and that actually enhances the rate of mixing. Okay, and that is why whenever there is fluid flow, apart from the solute gradient or concentration gradient, the rate of mixing in porous media gets enhanced significantly. Okay, and that is what is depicted here. So let's say this is the same system that you had here, right? And now you're going from that to this here, and here time is still equal to t1, but now there is a fluid flow. So this is with flow, right? In this case, you will see that this zone that you had before has become much broader. So if this is L2, that is now greater than L1 for the same time T1. So this T1 that you see is same as this T1. So for the same time, since the barrier was removed, the total length of mixing has become greater when there is fluid flow compared to when there was no fluid flow, right? And this happens because of this property called mechanical dispersion in porous media. Okay, so this thing that we see here, the effects of molecular diffusion and mechanical dispersion are actually quantified in terms of a parameter called dispersion coefficient, and that is something we already have seen when we saw the advection dispersion equation, and that is something we did in the last lecture, and I am going to simply copy the equation from here. Okay, so this is the equation that we have used, where u, v, w are the velocities in x, y, z direction, right? So u, v, w are the, let's call the velocity in x, y, and z directions. Okay, and d here that you see, d is known as the dispersion coefficient. Okay, and c obviously is the concentration, solute concentration. Okay, and this d that you see here within this x, y, z coordinate, that usually is a function of x, y, z. In fact, in this equation, many times these are written as, let's say, if the flow is primarily uh, in the x direction, then this can be called longitudinal dispersion, and this can be called transverse dispersion. Okay, but that takes us to much more complicated behavior of dispersion, and we are not going to go into full detail, but you can assume that many times this d is a function of x, y, z. However, for our case, we will consider it to be mostly constant in all directions. Okay, so now this d that you see, the dispersion coefficient, is actually defined as alpha U plus dm effective. And what do you see here is the effects of mechanical dispersion and molecular diffusion. Okay, so this actually uh, gives you the effects of mechanical dispersion, and that is something what we exactly just discussed. Whenever fluid flow happens through this pore scale medium, there is mixing of this or enhanced mixing of a solute in the fluid, right? And what you see here, this is the molecular diffusion. Okay, and d here can be called the dispersion coefficient, or in general it's also called hydrodynamic dispersion coefficient. Okay, so this d is a combination of both mechanical dispersion as well as molecular diffusion, whereas in this equation what you see here as alpha is something called dispersivity, and the unit of alpha is meter. Okay, and u is the primarily the longitudinal velocity, so that is the primary velocity in the medium, and dm effective is the effective molecular diffusion coefficient, right? And why do we call it effective molecular diffusion coefficient? So if you recall, in this particular case, when you add this sugar to salt, it will mix with certain rate, right? And that rate will give you that will be based on the molecular diffusion coefficient. But now when you try to repeat this process in porous media, the same molecular diffusion coefficient may not work. Why? Because now the flow is not happening, or mixing is not happening in straight path, rather there are tortuous paths. So when mixing happens, the solid molecules itself cannot just go straight, because it will always hit the solid particles within the medium, so it will go through these tortuous paths. And that is why this effective molecular diffusion coefficient in porous media is actually little different from the actual molecular diffusion coefficient, and this is usually given as dm effective to be equal to dm over tau. Tau is known as the tortuosity, so tau here is tortuosity constant, or you can call it coefficient, and that is defined as L over Le over L. Let's say that is the path traveled in porous medium over the straight path without the medium. Okay, so to understand this, let's consider that this is a porous media we have, right? And these are different porous particle, and now when you have a solid molecule or fluid molecule, when it wants to travel from point 1 to point 2, it will actually go through certain path like this, right? Whereas if it was not a porous medium, it would simply travel straight from this point to that point, right? So in this case, this is actually covering a distance of LE, whereas without porous media, it would be covering a distance of simply L, right? So this distance, this LE over L, is generally known as tortuosity, because LE is little greater than L, because now it is going through this tortuous path, and that is why tau value is usually greater than 1, but still it is in order of 1. So it is greater than 1, but not significantly greater than 1. Okay, so many times you can also consider to be close to 1, and you may want to neglect the effect of tortuosity if needed. Okay, but this is what you have to consider to define the effective molecular diffusion coefficient in porous media. All right, so here we have seen the total dispersion coefficient in porous media is defined as alpha u plus molecular diffusion coefficient, where alpha is the dispersivity, and that depends on the medium. This is something that can be obtained only experimentally. So I would say this is an experimental parameter. This cannot be predicted theoretically. Likewise, your tau is also an experimental parameter. Okay, so now this thing we have seen that your total dispersion is happening both because of mechanical dispersion as well as molecular diffusion. So we have to figure out in which kind of conditions your mechanical dispersion or effects of mechanical dispersion is more, or in which condition your effects of molecular diffusion is more. Okay, so to be able to do that comparison, there is a number called Peclet number, which is generally written as P, and this gives you the effects of mechanical dispersion over molecular diffusion. Okay, so this gives you a relative comparison of these two different processes, which obviously happens together, but the total mixing that is happening may be happening because of molecular dispersion, or sorry, because of molecular diffusion or mechanical dispersion, right? So this one is basically alpha u, and this one is dm, right? So Peclet number can be defined as alpha u over dm tau. So this is, let's say, the effective. So this can be written as tau alpha u over dm. Okay, so that is your Peclet number, and this is a dimensionless parameter. Okay, so Peclet number is dimensionless and gives you the relative importance of mechanical dispersion over molecular diffusion. So if Peclet number is much greater than 1, the mixing happens primarily due to mechanical dispersion. Okay, or in other words, your mechanical dispersion is much greater than molecular diffusion, right? That is much greater than 1 regime for Peclet number. And if Peclet number is much smaller than 1, in that case we can assume u to be almost equal to 0, especially when velocity is very small. In that case, usually Peclet number is much smaller than 1. In this case, mixing occurs primarily due to molecular diffusion, right? Or in other words, your molecular diffusion is much greater than mechanical dispersion. All right, so these are two different regimes in which mixing in porous media happens depending on the values of Peclet number. And we are going to see both the cases one by one in the coming lecture.